In today's video, we're going to look at the concept of specific latent heat and see how to use it in calculations. We saw in the last video that as we heat up a substance, the particles gain energy in their kinetic energy store, and this increases their internal energy. We also saw that the temperature is just a measure of average internal energy of all the particles in a substance. So as we heat objects and the internal energy of their particles increases, the object's temperature rises as well. The whole point of this video though is that there is an exception to this rule. This occurs when there is a change in state. If you take a look at this graph, which shows how the temperature of a substance changes with time as we heat it, you can see that it is not a straight line that you might expect. This is because when the substance changes states at the melting point or the boiling point, the energy that we are providing is being used to weaken or break the forces holding the particles together rather than increasing the particles' internal energy. And remember that the temperature is just a measure of the average internal energy of the particles. So in this case, the overall temperature won't change in these regions until all of the substance has changed states. The same principle applies if we look at a similar graph for cooling a substance. This time though, the state change is different. Since it involves the formation of new bonds between particles which releases energy and so counteracts the cooling, and this is what keeps the temperature constant during the changing state. Now, the exact amount of energy that is required to change the state of a substance while the temperature remains same is called the latent heat. The standardized word for it is specific latent heat. It is defined as energy required to change the state of 1 kilogram of a substance without changing its temperature. And it depends upon two things: the type of substance and the amount of substance used. It has two types. One is specific latent heat of vaporization, which is energy change where substance changes between a liquid and gas, so it either evaporates or condenses. The other is specific latent heat of fusion, when a substance changes between a solid and a liquid. Therefore, it either melts or freezes. To see how it works, we take the example of water, which is heated from minus 50 degrees Celsius, where it was solid ice, to 150 degrees Celsius, where it is gaseous water vapor. As we heat 1 kg of ice, particles all gain internal energy, and so its temperature increases. However, once we reach 0 degrees Celsius, the ice starts to melt, and because all the heat energy that we are supplying is being used to break the forces between the particles, the overall temperature stays the same. The energy required for this stage is the specific latent heat of fusion, and in the case of water, this is 3,34,000 joules per kilo. Once this much energy has been provided though, and the ice is all melted into liquid water, and then the temperature will continue to increase all the way to 100 degree when the same process happens again. This time though, the energy required is the specific latent heat of vaporization, which is 2,260,000. And once the water has all boiled into water vapor, its temperature continues to increase like normal. Now remember kids, you don't need to memorize these figures, they will be provided to you in the exam if they are needed. If we were to cool our water, same concepts will be applied, but the amount of energy mentioned prior for vaporization and fusion would be the amounts of energy released rather than required at each stage. The last thing is the equation. The equation tells us that the energy required or released is equal to the mass of the substance times the specific latent heat. We can see this equation in a triangular format as well. An example question includes how much energy is required to completely boil 2.5 kg of water at 100 degrees Celsius. We will use the information that we have been provided in the table. The mass of the substance is 2.5 kgs and since we are boiling the liquid, we will use specific latent heat of vaporization. By multiplying these two figures together, we will get the product, that is our answers, 5,630 kilojoules. Thank you.